So we talked about auxiliary lines before. There's kind of an interesting that can happen. Let me draw a triangle here real quick. You, and let's bring it down here, and bring you across. Now here we've got ourselves a triangle. I'm going to extend with an auxiliary line one of the sides. So you can see what I've done there. I've just taken this bottom edge and I've extended it out. It didn't have to be the bottom edge. It could have been any of the edges. But what happens here, this angle that's left over, kind of highlighted in pink here, this is called an exterior angle. And it's an exterior angle because it's on the outside of the triangle, but it's still made by using two sides of the triangle, right? The bottom side and the right hand side of the triangle still make this angle. That's important. If I were to have just some random line coming out here, now that one looks like it might be extended to the other one. If I just had some random line coming out here, it's not made by two sides of the triangle, so it's not really related to the triangle at all. Um, but that exterior angle does have a relationship with the triangle itself. If we take a look here, that exterior angle is always going to be a linear pair with the piece inside because it makes a straight line. So there, this is always going to be a linear pair. That's useful because the sum is always 180. What's interesting though is we have these two other angles here. Do you see how they're removed from the exterior angle, that are not adjacent to it? We call these the remote interior angles. And the remote interior angles are always equal to the exterior angle. So remote interior angles equals, so the sum of the remote, the exterior angle. So if this is angle 1, angle 2, angle 3, and we'll call this angle 4, what this looks like is measure of angle 1 plus measure of angle 2 is equal to measure of angle 4. Okay, so that's the relationship that I'm going to be using here. And that's actually a theorem. Use the exterior angle theorem. I don't know why I didn't write that, copy and paste that in, but it is in your book. You can look it up. Let's take a look and use this theorem in an example. Find the measure of angle JKL. JKL. Alright, so that's the angle we're looking for. It looks like it's got an expression in the triangle pose shown below. Of course, the triangle pose is a yoga pose. So what we're going to do is here, angle JKL is an exterior angle. Angle L and angle M are remote interior angles in relationship to JKL. So I know that the remote interior angles should add up to be the exterior angle. So angle L plus measure of angle M should add up together to be the measure of angle JKL. And all we have to do is plug it in. Angle L is X, measure of angle M is 50 degrees, and JKL is 2x minus 15. And now I go ahead and solve my equations. Subtract x from both sides. 50 equals x minus 15. Add 15. X equals 65. Now I double check, is that what they want for my answer? Sometimes it is, sometimes it isn't. And in my problem here, it asked me to find the measure of JKL. So that's not my answer. I want to plug it back in. But I know the measure of JKL is equal to the expression 2x minus 15. So all I have to do is plug in 65 for x. That's going to be 130 minus 15, or 115 degrees. And that's the measure of JKL.